We're going to talk about inverse trig functions. For the most part, we're going to be using these functions to solve equations, which we'll do in the next section. But to start off, we need to come up with some really good definitions of these functions, particularly ones that give us unique solutions. Let's go ahead and start off with sine inverse. There's two ways to express these inverse functions. One of them is kind of what you'd expect, and that is with, let's see, this is going to be sine to the -1, but it's read sine inverse of x. I'll just give an equation there, equals y. But we can also write this as arc sine. So arc sine of x equals y. For these, the input is not an angle. The input is a trig ratio. Let me go ahead and write that in the box down below. So regular sine is applied to an angle measure, and we get a trig ratio back. And when I say trig ratio, I'm thinking about SOHCAHTOA. SOHCAHTOA, so would be opposite over hypotenuse. So I'm thinking of that. Let's see, there's my angle. So opposite over hypotenuse is what I'm thinking through. That's what sine gives us. Sine inverse, though, does just the opposite. So sine inverse, we're going to put in a trig ratio, and it's going to return the angle measure. This is really, really useful when it comes to construction in particular. If we need the corner of a wall to be a particular angle, it's hard to measure an angle, but it's much easier to measure distances. We can measure those distances and then use an inverse function. Let me put that inverse there on the sign, an inverse function to come up with the angle that we need. Domain and range of our inverse function are exactly reversed from that of my sine graph. So what I've got here is the traditional sine graph. You'll notice that in the sine graph, those trig ratios, which are the y values, so all of these are the trig ratios, they're bound by -1 to 1. Well, the trig ratios are what go into an inverse function. So my trig ratios, the domain, are bound by -1 to 1. Next is the range. The problem with the range, these are my angle measures, is that we have these repeating values. And so whenever we come up with some kind of a trig value, a trig ratio, and we line it up with an angle, that shows up multiple times. So we're going to go ahead and limit this. And the math rule decided to limit this so that there are no repeats between -π12 and π12. And you'll notice that as soon as I turn the corner, I end up getting some repeats. So we're going to limit, this is by definition, we're going to limit the range so we can only get outputs between -π12 and π12. I think a really nice way to look at this is on the unit circle instead. On the unit circle, -π12 is here on the negative y-axis. π12 is up here on the positive y-axis. Sine values are y values on the unit circle. So we're really limiting these from y-axis to y-axis. So what I've drawn in green there are the possible outputs or the range of sine inverse. Let's work through some examples. For this first example, I can rewrite this as saying the sine of what angle, because all of these answers are going to be angles. The sine of what angle is equal to radical 2 over 2. Well, you should recognize that as a π4. I'm just going to make sure that π4 is within my range, and it is. π4 is right there. So I can go ahead and use π4 as my answer. So I get the angle back. The next one, again, I want the angle back. So this says the sine of what angle is equal to, let me get that π4 out of the way, is equal to negative radical 3 over 2. Well, you should recognize this one as a 30, 60, 90 triangle. Radical 3 over 2 is going to be the bigger length. So we're dealing with a triangle that looks like this. So I want a 60-degree angle, and I want it to be where I have a negative radical 3 over 2. Well, in my range, I need to put it over here. I could have drawn it over here, but that's not within my range. So to get the angle in my range that I need to travel with a negative angle, and that's going to be negative pi thirds. You will get used to this, negative pi thirds. Yes, there are multiple angles, but to have a well-defined function, we need the angle in the range only. Okay, last but not least here, I've got the sine inverse of -1. There is -1. So I'm looking for the angle whose sine is -1. I know it's going to be, it's 3 pi halves if I could travel that way, but I can't travel that way. Instead, I've got to stay within my range. So I'm going to go negative pi halves instead. Negative pi halves. You can see this one, and I'm going to do the last one with your calculator. So the sine inverse is in blue, and I'm going to use my second function to get there. I'm actually going to put this in degrees just for a second because it's a little bit easier to see these answers in degrees. So if I put this into degrees, you're going to start to see really quickly that the calculator also needs a well-defined function. So I'm going to go ahead and do the sine inverse of -1. Now on the unit circle, 3 pi halves would work, but instead it gives me that negative 90 degrees. If I were to do the sine inverse, so sine inverse of negative radical 3 over 2, it's going to do the same thing. It's picking that well-defined output that is within that range that we've defined, and it's going to give me the negative 60 degrees or the negative pi thirds. So don't forget, I'm going to go ahead and put my mode back into radians. It's such an easy mistake to make, so I'll put that back into radians just so I don't forget. Okay, back to our worksheet. Now let's go ahead and do the same for cosine. So cosine is going to get defined the same way. So I can define that as cosine inverse of x, but we can also write that as arc cosine. Let's go ahead and start just with regular cosine. Regular cosine gets applied to an angle, and I get a trig ratio back. Again, I'm thinking of SOHCAHTOA. This would be adjacent, opposite, and hypotenuse angle. SOHCAHTOA, so ka for cosine is going to be adjacent over hypotenuse. So those are the trig ratios we're looking at. Cosine inverse gets applied to the trig ratio and gives me an angle back. Okay, same story. To get the domain, I need my outputs, all the possible trig ratios. So all my trig ratios, well, these guys are bound between 1 and -1. These are fractions of the lengths of those sides. So they can only be between -1 and 1. Of course, unless there's a transformation, right? We've seen that. So -1 to 1. The range are my angle measures. These need to be well defined so we get just one answer back. The math world decided to make these well defined and only go between 0 and pi. And again, you'll notice as soon as we turn the corner, we end up getting duplicate values. So we don't want to do that. So we're going to go ahead and just limit it between 0 and pi. So my range is 0, pi. Again, I think this is easier to remember on the unit circle. Cosines refer to x's, my x-axis here. So if I go positive x to negative x, I also, in terms of angle measures, get my range. So I'm only ever going to get angles between 0 and pi when I apply a cosine inverse. Let's go ahead and start with part A, -1/2. -1/2. So I'm looking for a cosine. -1/2 would be right here, actually. It could be a negative. Sorry, not a negative. It could be in quadrant 3, but instead I'm going to choose it to be in quadrant 2 so that my angle lives within my range. So this has got to be 2 pi thirds. Cosine inverse of 1. 1 lives right here as a cosine value. I could describe that by using 0 or 2 pi or 4 pi. lots and lots of different answers, but when I apply cosine inverse, I'm looking for the unique answer between 0 and pi. So the angle is going to be 0. And again, we can check that. The cosine of 0 is equal to 1. Finally, radical 2 over 2. So the cosine of what angle is equal to radical 2 over 2. All of these outputs are angles. Well, that's got to be a pi fourths, and that does live within my range, so I know to go ahead and stick with my pi fourths. It's going to be this guy right here, pi fourths. Tangent, same descriptors here, so it can be expressed with a tan inverse or with an arctan. And I also do the same swap between my angle measures and my trig ratios. So tangent originally applied to an angle, and it gave me a trig ratio back. SOHCAHTOA, OA, so that would be opposite over adjacent. If I write that instead as the inverse function, we get tan inverse of theta. Oh, sorry, tan inverse, not of theta, did you catch that? Of my trig ratio is equal to theta. We need to do the same thing and worry about restricting our range and domain. I know on this graphic that I have here, and this is just for tangent, X, and then X is here. They do have this dotted line here, but it really doesn't mean anything. These tan curves go up forever. Grab my red pen there. They go up forever. They happen to be asymptotic, but they do go up forever. So those trig ratios could be anything. So this would be all real numbers. The range, though, those angles do need to be restricted, and we're going to restrict those between negative pi halves and pi halves. Since there are asymptotes there, I can't actually have those angles, so I'm just going to put those in parentheses, negative pi halves to pi halves. It's kind of nice because it's really the same restriction that we had for sine. So if I go ahead and take a look at this, negative pi halves to pi halves, it again goes from the negative y-axis to the positive y-axis, pi halves. Let's go ahead and find these values. So we've got tan inverse applied to these values. So remember, my outputs are going to be angle measures. So for the first one, I want the tan of what angle is equal to -1. Well, to get a 1 or a -1, I have to have a 45-degree angle. So to get a tan inverse of -1, or a tan to be -1, I would need to have it either here or here would work as well, 45-degree angle. So to get that to work out, I need a negative pi fourths. If you wanted to do the math here, opposite would be, opposite would be negative radical 2 over 2, adjacent is radical 2 over 2, and that's how you get that -1. The next one is negative again. So to get a tangent of negative, I know that I'm going to be here with a negative angle, and I want a radical 3 over 2. That radical 3, let me first write this as tan of what angle is negative radical 3 over 3. That radical 3 tells me that this must be a 30, 60, 90 triangle. As I think about tan of theta being sine over cosine, that tells me that I want the radical 3 to be in the numerator. So radical 3 over 3. So this would be, let's see, if I think this guy through, this is rationalized. It's a tricky one. 1 over radical 3. It's that rationalized. So if I want a radical 3 in the numerator and radical 3 in the denominator and a 1 in the numerator, and then we've got a negative floating around here, then this has got to come from over 2 over 2. So it's got to come from the angle where the sine is going to be that -1/2. So sine is my y value. So sine is -1/2. That's going to be this guy right here, negative pi sixths. The next one's actually really similar. So this is a nice one to follow up from. So if I want this next one, let me write it over here. So part C, tan of what angle is radical 3? I know that that's going to be in quadrant 1. So I can say that the tan is the sine over the cosine. Radical 3 over 1. And if I fill those in with the over 2's, this now is going to give me a sign that's going to have the larger value. It's going to be my 60-degree angle, or pi thirds. Whew, those are a little painful to think through. You can always use your calculator, switch it to degrees. I'm in mode. So I'm going to go ahead and switch that to degrees. Enter, and then let's go ahead and quit here and do a tan inverse. So I'm going to go second, tan inverse, and I just did the radical 3. So let's go ahead and check our radical 3. Square root is right there, 3, enter, and it gives me 60 degrees, which would be pi thirds. So a really nice way to check those.